Okay, so the next speaker is Professor Vieri Mastropietro from University of Milan, via Saldini, and the title of his talk is Chiral Lattice Gauge Theory, Anomaly Cancellation, and Universality.
So, okay. So first I want to recall the first time I've seen or I sent a mail to Sergio that I was just arrived in Milano in the mathematical department. So there I have a lot of friends there, but I mean, there I can only speak about classical mechanics. So I could not speak about something I like, critical exponents, renormalization group, fermions. So I felt alone. so probably Luigi Galgani, which is a sort of senior there, understood I was feeling alone there, and they said, so write to Sergio Caraccio. Yeah, sure, yes, do that. So I just wrote, so I follow his advice. So I said, if I trust you, and then I got this wonderful paper with, which is in the title, All the Things I Like, Forests, Trees, Fermions. I mean, I was so I was very happy of this paper. Then I felt at home, in a sense, only after seeing that was some. So we didn't have a lot of interaction directly, but indirectly, I mean, the presence of Sergio arrives as water waves up to Via Saldini, and I felt, I mean, at home there because just he's in the physics department. Then, I mean, I keep this paper for 10 years because I was hoping to do something with that. Then I wanted to discuss with Sergio for all these years that we could not. Then I was in Princeton this year for all the semester, and then a big fraction of my time there was just devoted hearing seminars about this paper, which is the mathematical physicists now are Spencer and Bauer Schmidt and very much interested. There are also the other authors, so are very much interested in these things. So at least 3 talks were using this representation of the Potts model with Q equal to 0 in terms of fermions. So I mean, is still I hope to. I mean, the easy things that I wanted to do was already done. Unfortunately, I heard in these talks, but I hope in the future to come back. So this is my first interaction. The second is that I'm taking this statistical physics course, which was the course of Professor Caraccio before me. And then I receive all his students. So I'm exposed, of course, to his influence. And I mean, the students here are former students here. So they know that I always ask them, I mean, what Caraccio teach about this, how say that. And so I want to be. So for me, it's a sort of gold standard, difficult to reach, of course, but I mean, it's a gold standard. So I'm very happy to be here to celebrate. And I hope your influence, I mean, as I said, I mean, like Rings water, which arrives up to Via Saldini from there, and it's a very good influence. I hope this influence will remain, I mean, in the future. Okay, so I hope this talk will like him. I think here there should be all the ingredients that should like him, because there are gauge theories, there is anomalies, there is a renormalization group, there is Wilson, there is I tried this. Anyway, you will see. Okay, so let me start from something very standard. So the consistency of the standard model relies on the vanishing of the chiral anomaly for the U1 and SU2 sector. So this is really crucial for even the renormalizability of the theory. If the anomaly does, the standard model is a chiral theory, so the current is chiral. So if there are anomalies, they break the gauge symmetry, which is at the basis of the model. So it's a big problem. So in fact, if you consider just so this is a famous sort of mystic graph, which is the triangle, right? So if you compute the axial vector current, you will see that you get the difference of the hypercharge to the cube for the left and right particles. Then you need that this object is 0, right? Because otherwise the current is not conserved. So this is very interesting because if you combine this and the other, so you need this condition, but and must be 0. This was found in the 72. And if you combine this condition with the other condition from the SU2 sector, then this constrains the value of the charges It's almost the charges of the particle are almost constrained. So for instance, they are all multiple of 1/3 the charge of the electron. So you have charge quantization without grand unification. So this is very subtle, right? So you need, the theory itself tells you that the charge of the quarks and of the leptons must combine so that this condition is true. So without this condition, of course, the atom, just to, I mean, young people, I want just to recall that if the electron and the protons would be a very teeny difference in the charge, I mean, all the world disappears. So I mean, this condition is really important. But this is found only for this graph. So what happens if I put all the possible graphs? So you will have all the possible kind of decoration here. So it becomes a mess. Okay, if you put quantum fields. If you have quantum fields, you have to decorate everything. So now there is a famous result by Adler and Bardeen of '69, which says that all higher order correction to the anomaly vanish. So indeed, if you get the condition with classical fields, then all the radiative correction go out. There are also the proof of Adler and Bardeen is just perturbative, just ordered by order. This means that one needs dimensional regularization, and dimensional regularization is impossible to make it non-perturbative. There are also non-perturbative proofs. For instance, this famous one of Fujikawa, but Fujikawa is not correct. It's very well known. This is just one loop result. So first, if you prove that one loop is exact, is a sense tautological. So it's even written in the review of Adler, but even in the textbook. So it is well known. So that is not correct. So now one wants, so let me recall also the issue of triviality. Unfortunately, Jurgi is not here, but anyway, triviality, the sector phi4 is believed to make trivial at least the electroweak sector of the theory. So it is expected if you remove cutoffs that the series are not convergent. So you must see the standard model as a non-perturbative standard model can be understood only on a finite lattice. Okay, but on a finite lattice, then you get this problem of the anomalies. You need that the same condition you get in the continuum is true also with the lattice and the non-perturbative level. So that there are a lot of attempts to construct this. So a prerequisite is that the anomaly at the non-perturbative level cancel with lattice with quantum interaction. Okay, so that's a problem that is a prerequisite. It's not enough to construct the theory with a cutoff exponentially small in the coupling, but it's a prerequisite. So there are a number of problems that I have no time now to explain, but in particular, there is a famous problem, is the fermion doubling, that if you put the fermions on the lattice, the poles increase, and then you have to kill the other poles by terms, for instance, which is called the Wilson term, but the Wilson terms breaks the chiral symmetry. And so, I mean, this produces problems. So these terms are irrelevant in the renormalization group sense, but they keep you finite corrections. Okay, so this can break the cancellation. Okay, so there are also lattice quantum field theory arguments, for instance, Luscher or Neuberger. But they are or ordered by order in the U1 case, or they assume the thermodynamic limit. Another attempt could be to use topological arguments, but topological arguments, to make them rigorous, needs mass. So again, they work only for one loop. So now let me go to another completely, so I mean, this is a problem then. So the problem, I repeat, one wants to prove that the cancellation, the anomaly cancel at the non-perturbative level with a finite lattice. And so let me go to another completely different field, apparently. So let me say, so then only perturbative or formal proof exist. So now let me go to condensed matter instead. So direct semimetals like graphene can be considered simulation of quantum field theory on a lattice, and the anomaly is related to transport. Okay, so the transport, the transport coefficient are very much related to the anomaly. Okay, so they can be considered experimental realization of a lattice quantum field theory. There is this very nice experiment which was done in the 2008 by the group of Gaim and Nozofelov. They were able to prove that the conductivity in graphene is pi over 2, okay, exactly pi over 2. So this is very interesting because there is, this phenomenon is different with respect to the all quantization, okay, which is really needs a gap. There is no topological explanation for this, at least up to this moment, no one has found. And this pi over 2 is exactly the value of the anomaly in the relativistic case without any correction. So it's a graph like this because we are in 2 dimensions. So it's a graph like this. Okay. So why this? I find it. So I hope it's clear the relation of what I'm saying. So if you go on a lattice, you will get this plus all the other terms. Okay. But then if you make this, because surely the interaction is present, the lattice and the interaction is present, but the experiment says that you get no corrections. Okay. So this is a fact. This is an experiment, and indeed, there is a lot of interest in the condensed matter literature to explain this fact. Because if you make computations using perturbative approaches, you get correction. So the prediction of theoretical physics was to get correction to this value, but experiment doesn't see correction in agreement with the other Bardeen, what you expect in the case of anomalies. Okay, so right, because so at the end this phenomenon was understood. So let me say again that there is no topological argument. Usually in condensed matter one uses topological arguments, but cannot be used in this case. So at the end, this was understood in 2012 by Giuliani and Port and myself. We were able to using a lattice, taking seriously the lattice, we are able to recover this experimental result in a rigorous way. So which is the point? The point is that the lattice gives you some irrelevant terms, and these irrelevant terms can produce correction. But then if you use an exact renormalization group, you don't have to neglect anything. Then you will get pi over 2. Okay, because typically people neglect some irrelevant terms. Okay, but if you don't do that, if you consider a full renormalization group with all the possible terms, then you get exactly the correct result. Okay, so now the idea is to try to apply this kind of analogy of the anomaly in the transport to the case of the cancellation of the anomaly. So of course there is a difference. You have to go to 3 plus 1, why instead graphene is 2 plus 1, and then you consider chiral interaction. So I want to consider now a simple model, which is just the U1 sector. Of course, if you consider SU2, it's much more difficult. Non-compact massive gauge fields, massless Wilson fermions. No Higgs, so just the fermions, and they put the gauge fixing. So the target theory, so the continuum theory that one wants to describe in the lattice is something like this, in which you have this D is, Y is the hypercharge, B is the fields, and then you see this B small b is 0, 1 or 1, 0 on left and right, depending if you are considering the left or right particle. So you have a single family, neutrino electrons U and D, with L equal to 1 and 2. In one case, you have only the left, and in the other case, the interaction with the left, and the other case, you have only the interaction with the right. Okay. So you see, I have also. Okay. So you see, I also put the R fermions of kind E1 and the L fermions of kind E2, but they are not non-interactive, right? There is no B there. So I find an approach which was called the Rome approach to the to lattice fermions, in which they suggest just to include also these fictitious degrees of freedom when you go to the lattice. In particular, there is a review of Testa, in which this is done. Okay, so this is the target theory. And so this is the current, right? The vector, so the current would be Y, the hypercharge, times the vector field, the vector current, and the chiral current. And then one has to remind that the left and right is 1 plus or minus gamma 5. So these are the currents. So this is the continuum theory. So now we go to the lattice. So now I consider functional integral because now it's well defined. So in fact, I don't know. So this is just a Riemann integral, a Riemann and the Grassmann integral. So everything is finite. I put anti-periodic boundary condition on the fermions. The lattice is step A and side L. So the number of degree of freedom is finite. So the interaction between the fermions is this expression. So the first line is just the discrete difference, right? The second line is what is called Wilson term. So this Wilson term kills the gauge symmetry. Okay. The B is a massive gauge fit, but I fix the gauge. So in fact, I will comment about that later. So this is a gauge fixed problem, which and then there is also a mass. Okay, so this is just a lattice model. Then the interaction is introduced in this way. You see, using this exponential, this big ordering, and then I put the E to the B, and J is simply an external field. Okay, so this is the model I'm considering. So the J is just the external field. I make derivatives respect to J to produce the current. B is the field. Okay, and then this V tilde is the other piece. So why I'm choosing this complicated stuff? So first of all, in the continuum limit, it reduces to the simple theory we have seen before. Moreover, I introduced the external fields in this way. Again, sorry, I forgot to say that I need also to introduce a VC. VC is a counter that is here. You see, VC is a mass counter term. Okay, anyway, I don't know. It's up there. I don't know if you see VC, right? VC is the mass because the Wilson terms breaks the Chiral symmetry. So if I want to have a massless theory without mass, I need to choose the mass in the Bayer action. Okay. So this theory is gauge invariant for the vectors, so but not for the chiral. Okay. So again, so I hope the model is clear. So the 2-point function is the derivative respect to phi. Then you have to make the derivative respect to j, j5, and so you have the vertex functions. So now I define the axial vector current. So this derivative with respect to j5, j nu, and j rho. And then I have the total is the sum with the y, which are the hypercharge. Okay. Then A is plus or minus depending if you have left or right. So this is the 3-point function, the object that we want to compute. So now here is a very important point. The current is conserved. Okay, the chiral current is anyway non-conserved by the Wilson and so on. But the chiral current, I define the things so that word identities for the vector current is conserved. So you have exact word identities, and that is very important. So you have exact word identities for the not only emerging. I mean, these are really lattice word identities for the current, but not for the J5. Okay, the J5 is just chosen. There is no natural definition for the J5 just because the Wilson terms kills the symmetry. Okay. So the first line is simply the usual things like this. And the other is just the conservation of the current. Okay, so the content term are chosen so that the theory is massless. This is the definition of J5. The J5 is, there is no, while there is a definition for the current so that is conserved, I don't try to conserve the current because I know that is broken by the Wilson term. Okay, so is this I define so that in the continuum limit it tends to the continuum current. Then the J5 are chosen. So you need to put a normalization to the J5 so that the charge carried by the J5 is the same as the charge carried by the current. I mean, the fact that you need a Z, a normalization is even in the perturbative Adler case, it says that you need to normalize in a proper way the axial current. Otherwise, you don't get the Adler-Dardin theorem. This again is a manifestation of the anomaly. While the charge of the vector is protected by the word identity, it's not protected in the case of the axial one. Even in the perturbative theorem of Adler, you need to renormalize the axial current in a proper way, just to ensure this condition here, so that the charge is the same. Okay, so with all this is the theorem. So the theorem says that for lambda, which is the coupling, smaller than AM. So of course I can get only cutoff of the order of the mass. So it's much less that one wants, but at least in this case, the series are convergent. Okay? So AM must be 1. So 1 over A, which is the ultraviolet cutoff, must be of the order of the mass. Okay? Of course, one would like to have much better. One would like to have, I mean, the construction of the standard model that I'm not able to do, but would be A should be exponentially small in the charge. That would be in the coupling. That would be the ideal goal. But at least in the limit, in the thermodynamic limit, with this condition of the lambda, up to smaller term, then you see the condition of the same condition as in the continuum, ensure the vanishing of the right-hand side in exactly. I mean, there is even no renormalization on the Y. You don't want at all renormalization on the Y, because otherwise all the arguments on the charge would be. Also, you don't want to do something which is done a la Polchinski, so you don't want to carefully choose the bare charges so that they go to the physical value. You don't want to do that, because otherwise you will not be able to construct the theory for any cutoff. Okay, so this is the result. So you see, the anomaly vanishes, and so let me say more quickly which are the ideas. So the ideas is you want to control at a non-perturbative level the 3-point function. So you don't have to expand in Feynman graph. This is completely forbidden. This is very well known, because if you expand in Feynman graphs, you will get n factorials. And if you get n factorial, you don't know if you have convergence. So you have to avoid the Feynman graphs. So the first point is, first you integrate the bosons. And then to integrate the bosons, you need to use this Bridges formula, which says that you don't want at all to expand the exponential of the B. Instead, you use the fact that the connected expectation of the exponential of the B are equal to the sum over all the possible trees, product of the V, and the V are the 2-point function, integral of something, which is very complicated. But this VT is a convex linear combination of Vy, and then this Vy is positive. So that's a crucial point. So you need to use positivity, okay? And then you can simply bound that the P is a probability measure. You can bound it by 1, and then you have only to integrate over the V, and the V give you the result without factorials. Because here, what we're using here, we are using that the trees are much less than the loop graphs. So the loop graphs goes as n factorial square. So divided by n factorials give you n factorial. Instead, the trees are n factorials time constant. So divided by the n factorials of the expansion gives you constant to the n. So the series is convergent. So once you do that, so this is the easiest. Of course, here I'm using that the boson says a mass. If I don't have a mass, it's much more complicated, but that's that. So no multi-scale analysis for the bosons. So also remember that once you don't have to, after this integration of the B, you get a fermionic theory with all possible powers, all possible monomials, not simply simple theory. You have quartics, sixtics, and so on. You don't have to eliminate no one of them. Otherwise, you will lose symmetries. Okay, so we'll have to keep everything. So after this, now you need to use a Wilson renormalization group to integrate the fermions. You integrate step by step, and you see, you will get a sequence of theories which has different wave function normalization for the left and the right, and different for the particle species. So the Z depends on the chirality and depends on the particle species. Okay, on the I is the electron, neutrino, and so on, and left and right. So they depend. This is a chiral theory. Then you have to divide the potential in a relevant and irrelevant part, and the relevant part is simply, as the theory is super normalizable in the infrared, you have only the renormalization of the mass and of the currents. Okay, so once you have done all this, okay, then you have to make this expansion in Gallavotti trees, and then you have to use that you have to use that the expectation of fermions is given by a formula very similar to the one of the boson, except that now you have a determinant. And here again, you have to use a famous argument of Caianiello, which says that the fermionic perturbation theory is convergent because it's given in terms of determinants. And then you have the cancellation of determinants. So again, the expansion in fermions is bounded by Cn. Okay, so in the bosons, by positivity. For fermions, because they are fermions, so they cancel. Of course, you don't have to expand the determinant, otherwise you are lost. Okay, so again, you don't get any factorial. So now the crucial point is that you will get a sequence of potentials living on different scales, which has the correct power counting bound without n factorials. And even more important, that is really the crucial point, you will get this, this improvement here, which tells you that if you have to distinguish between the contribution of the kernels of the effective potential, the terms which has only relevant terms and the terms which are obtained by the contraction of irrelevant terms. The terms obtained by the contraction of irrelevant terms has an improvement, and that is very important. This theta I says that theta I is 1/2, for instance, when you have a contribution from R. Again, you don't have to eliminate anything. So now, all these renormalizations are finite, and they are given by convergent series. So we are coming to the end. So at the end, the 3-point function is divided in 2 pieces. So make another picture. You have 2 pieces, and then I'm almost finished. You have one piece, pi A, which is simply this, which is essentially the same graph, but with dressed propagators, plus MS, okay, which has all the possible graphs. But the difference is that this pi B, which is a mass of terms, is differentiable. While instead the first term is just continuous. So all the point of the anomaly is that the 3-point function is not is continuous but not differentiable. So PB, the second piece, has continuous derivatives. PA, which is the graph, dressed graph, is just continuous but without continuous derivatives. So that's the crucial point. Okay. So if the graph, all the properties of anomalies depends on the regularity properties of this function. So if they are differentiable, no anomaly at all. Instead, if they are continuous but with non-continuous derivatives, then you can have the anomaly. It's just due to this, the anomaly. So we separate in dupes. Okay. So this pi A is very complicated. It's a sum of all this kind of Y and zeta 5. So it seems very much non-universal. But now you use this Z, you use the word identities for computing this Z, because this zeta J are the dressing of the vector, and the dressing of the vector as word identities. Okay, so you get this exact relation, because remember that the vector current is exactly conserved. Okay, and then it simplifies a lot, and then you get that the dominant term is this form. So this is apparently strange, because now you started from a lattice theory, and now you get a theory which has a dominant piece the triangle graph with momentum regularization instead of lattice. So this looks bad, because now this doesn't conserve current. Okay, because now if you have a momentum regularization, it doesn't conserve current. Okay. So its frequency is continuous, and then R is a complicated series term. So, but now here's the crucial point. So you see, the dominant term doesn't conserve current. You see, P1 nu E nu is not zero in general. Instead, if you do the same for the triangle graph on the lattice, of course you get 0 here, because the current is conserved if you consider the vector current on the lattice, but not on the momentum cutoff. But now you use the fact that you can expand this R. Okay, so pi is the 3-point function. The first piece is not is just continuous but non-differentiable. R is continuous and differentiable, so it can expand up to the first order. And then, so I can arrive to the first order. I can expand E, but I can expand the R. So now I use the word identities for the current of the J row, or the row components. So I get condition of these derivatives. And now if I put this conditional derivatives in the final relation, then I get the result. Okay? So this concludes the proof. So once you have this decomposition, and when you have all this model defined so that the vector current is conserved, then you have done. Okay, so you have this. So of course, so this concludes. So so the conclusion then is, so if it was too quick, I can repeat, because I think it's a very elementary. So in a sense, if you accept this for, so let's say, so you have to move to. So all the point is to get this formula. Okay, this one. So you want to write the 3-point function as a piece which is equal to the non-interacting theory with the momentum regularization, plus a piece which is a mess but is differentiable. Okay, and then you fix the derivatives by the condition that the current is conserved. So as I said, it's very, very important that you don't neglect the relevant terms. If you eliminate some irrelevant terms, you don't have any more these conservation rules. So you must keep all the possible relevant terms, or this W are series. You don't, if you neglect a single one of them, you don't have any more the cancellation. But as this remessage is exact, we don't eliminate everything. So it's just like this. Okay, so this is the conclusion. So the anomaly vanishes at a finite lattice at a non-perturbative level with the same condition as in the continuum. So that is a prerequisite for a lattice anomaly-free construction of the electroweak theory. So the strategy is inspired by the results we got for transport coefficients in graphene or Waldseeming metals. So you see, it's exactly the strategy we have used to explain these experiments in graphene, where it was found in universality, even if perturbative computation don't get universality. Okay, that's the really delicate point. All this approach I can control. So it's like, so this is at the level of the old theory of Fermi. Okay, the old theory of Fermi works, is non-normalizable. So it works up to a cutoff of the order of the mass of the boson. This is the same kind of things. If you want to improve, so that's the theory of Fermi is perfectly well. Simply that you cannot go to 1/A greater than the mass, but the technique can be used. So now next step, I don't know how, probably it's very difficult, but the next step is try to decompose also the Bose field. Okay, so if I perform a multi-scale decomposition also for the Bose field, then the theory becomes normalizable, but not asymptotically free in the ultraviolet. But they can arrive to exponentially large cutoff. Exponentially large cutoff are very large. If you put the inverse of the weak coupling, and then you see the exponential of that is enormous, so it would be okay. Of course, it's very difficult in this approach to make a multiscale analysis of the bosons. Okay. So the open problem is that to get a realistic exponentially high cutoff, one needs the multiscales also for bosons. But all the point is that when you need the anomaly cancellation so that the non-decaying terms give no contribution to the value of the kernels. Okay, so hopefully this anomaly cancellation condition would be enough to kill the non-decaying part. Then don't produce a non-normalizable power counting and then get this. But it's not done. But at least I think is and then of course extension to SU2 would be very difficult. But again, I think this is a result in which at least is reassuring that the anomaly cancel with the same condition as in the continuum at the non-perturbative level. Okay, so without any assumption. So you consider a scale like that, small coupling uniformly in the volume, all the series are convergent, and then really you don't have to make any fine tuning. So the Y are exactly as in the Bayer case, because if you have to make a fine tuning, this means would be strange, right? So you want to prove quantization. So quantization of the charge, you don't have to fix the Bayer charge to the. Anyway, so I hope it's clear. So it's late. So
Questions?
Okay. The standard model is not believed to have a continuum limit.
Right?
The standard model is not believed to have a continuum limit. Okay, so there is no any fixed point in the statistical field theory on the lattice and so on. So the standard model is believed to be essentially defined at the perturbative level. That's it. Because there is no a continuum limit. So there is a non-perturbable formulation.
Yes.
So you are proving something at non-perturbable level.
But yes, as I said,
you understand
perfectly, just let me answer. So of course, the point is, if you want really to remove and take the continuum limit, that's for sure is defined only at the perturbative level, just by triviality. So it's not a technical problem. One believes that cannot be made. On the other hand, one can take the point of view of effective quantum field theory. One can say, well, that's the standard model is a model which is correct up to a certain scale. But up to that scale, one wants to construct at the non-perturbative level. So the higher is the scale, the more difficult is it to construct it.
Yeah, maybe you are right. But the point is that I think that it remains a formal proof because there is not a non-perturbative formulation. Even though
this functional interest is well defined with data
of
present.
course, it's well defined. I think that's the continuum theory is not.
Yeah, as I said,
level.
So maybe it's not clear. The continuous limit, I'm not speaking, I'm just fixing the A. So my point is, if I can arrive to a 1 over A is the energy scale. Okay, so the whole Fermi theory, it is true up to an energy scale, which is the electroweak cap, right? So it's the mass of the W, okay, which is not very high. So that is the scale when I can arrive. If not all the standard, I'm just speaking about the electroweak, then the QCD is another stuff. But QCD is yeah, but anyway, I'm not studying about that. If the electroweak, yeah, it would be for other reason, but the electroweak is a weak coupling. Okay, so if I can arrive to a scale which is the exponential of the inverse of the scale, and get a non-perturbative construction of that, I mean, that would be something interesting for me. So I would like to arrive to an inverse lattice of the order of the inverse of the electroweak coupling. It seems to me possible. Yeah, is it effective? Yes, in my point is the defective point of view. So I want to arrive to the maximal possible cutoff to give a non-perturbative meaning. I'm not, for what I cannot, but that's, I think even Weber now, before dying, was saying that the standard model is an effective theory. Yeah, so it's an effective, but so I want to, but even the effective theory is not obvious to construct. This is what I mean. It's not that it is on the lattice and then it's obvious, because of course you have to take the infinite volume limit. So it's in infinite dimensional. So I want to construct the electron. If I succeed here, I construct the theory at the order of a cutoff, which is the order of the mass. I would like to arrive to exponentially high cutoffs. That's for me I cannot arrive to the Landau pole, but I want to arrive before the Landau pole and give a non-perturbative formulation as an effective field theory. This seems to me an interesting, the best you can prove. Well, it's not very satisfactory, sorry, and then stop to say it's just a formal series, because one could say a formal series of what? What it means. So it's a series of what? Right? So you say it's just, as a mathematician, what means a series of nothing? I mean, right? It works, but if it is asymptotic, you don't have really a fundamental theory. Right? So in this way, you get a fundamental object. So anyways.
Other questions? Okay, if not, let's thank again Professor Mastropietro. I think it's all for today. We resume tomorrow at 9 a.m.